Hello everyone, welcome again. It's 2023 and I thought that what is the best way of starting a new year? So probably with a new tutorial. So today I bring you a new tutorial related to data calibration in this case. So I hope you will find it interesting. Before starting, just mention that I'm trying a new setup with a camera over there and screen over here. That is the one I will use for sharing all the content, and also a new microphone that I hope will help with the audio quality. Okay, so then without further ado, let's start with the tutorial. I will try to make them shorter from now on, so I think it will be easy to follow them and then just go back to them and find things relatively quickly instead of going through 1 hour tutorials. So let's start. The first thing is just let's make this much smaller so then you can see me, but still you can also see the screen. I will put it around here. I think that's fine. And then let's start with the presentation that I prepared for you. The idea is, so I want to start a new series of tutorials. These are related to preparing the data to be used on inversion codes like SER, design, or other codes that you can have in the literature. So the idea is that we are going to cover some specific steps that we can do when we get data from a telescope. And step by step, we can add a more complex process in terms of going back to the basics that you sometimes need to do when you get data that has not been too much modified by the telescope team. So then, in this case, it's going to be very simple. As I said, it's day one. So we are going to focus on the continuum normalization, but in particular in two things. So normalizing the data that you get, and also including the effect that if your data is not at this center, you need to rescale your normalization, including the center to limb variation. Okay, so then what we have is we are going to learn how to normalize an observation. Okay, we are going to assume, as I said, that most of the calibration steps that usually you need to do, like flat fielding, alignment, and other things, are done. So we are going to assume that you are somehow close to what we usually call level 1. And we are going to analyze or to prepare the data to be used for inversions to get to something that we sometimes call level 2. Okay, so then our task is to normalize the Stokes profile to the format used by SER on Desire. I will usually exchange the name SER or Desire, but it's usually the same format, so it is valid for both codes. The next step that we are going to talk about it in this presentation, but it's going to be a part of day 2 because I thought that it could be too long for just one tutorial to do everything. But the important thing is that you need to do this mainly when you use ground-based telescopes. So for example, SST, Gregor, or DKIST, because you have an spectra that contains transitions or spectral lines that are from solar origin, but sometimes you also have transitions that are from the atmosphere, from the Earth, that are what we call telluric lines. And these ones, you don't want to have them in your inversion because the code usually doesn't know about those lines, and then they can interpret, and the code can interpret them as an effect, a shift, or maybe some perturbation in the spectrum that is not from solar origin. Okay, so then the steps that we are going to follow today is just for simplifying the process. We are going to use the atlas. You can download them from this web page. You can just click and go there. We are going to go in just 1 second. And we are going to focus on the spectral region at 630 nanometers. The idea is that this is the one that you see here. So this region is very famous and has been used since a lot of years, maybe since late 80s. And it's very famous because it contains two iron line transitions that are relatively easy to model. They work relatively okay in LTE, and they have been observed a lot with the spectropolarimeter on board Hinode since 2006. So we are used to use these lines for interpreting the magnetic field in the photosphere. But in the case of the ground-based telescopes, you have these two thin lines here that, as I said, they are from the Earth atmosphere. So you don't want to have them in your analysis, because the code will interpret this as maybe a second component that is very Doppler shifted, or maybe will struggle to try to understand what is happening there. Don't worry, because we are going to reproduce these issues, but the important thing is that I want to start with an example that is very close to what we usually use, and something that you will use with the first data coming from the keys from the VISP instrument. It will observe this spectral window. Okay, so what we are going to learn, as I said, is first to normalize the spectrum. So for example, in this case, the atlas, you have that it says 10,000 units and it says normalized intensity, but it's an arbitrary normalization, so we cannot use this for zero desire. And then we are going to assume a case where you have observed this spectrum, but a heliocentric angle that is not this center. So we are going to learn how we can model this. And finally, we will remove these telluric lines from the inversion, but this will be done, as I said, in the second day. Okay, so then let's go to the atlas and let's download it. Just 1 second, I will go there. So yes, it's here. So this is, just 1 second. So then we go to solar spectrum. And then we have here the spectrum. Just make this a bit bigger. And we type here 6301. And then here we put like 2 Armstrongs. And sorry, 602. And here you will get the same spectrum that I was showing you. And the idea is that for download it, just click in this icon here. And then it appears, our second window will appear, and you have the wavelength in Armstrong and then the counts in this normalized arbitrary normalization that they have. Just as a note, they said here that each value is normalized to the local continuum and is set to 10,000. Okay, so then you can just copy this in a file, but I just did it for you. So then let's go to a folder where we are going to work. So this folder is in the Dropbox folder that I always share with you. So you will be able to see everything that is here, in here. And this is the file that we have just created with the information from the atlas. And now we are going to work with this ideal procedure that I called data calibration. Okay, so then let's open it. I will just minimize this for a second. And this is where we are going to work from now on. I went back to IDL. I thought that I could do these tutorials in Python, and I think I may be able to do it, but I feel much more comfortable with IDL, and I think I do things much faster. But the idea is that all the steps that we are going to do are very simple to follow. And also I already created some routines in Python for reading, writing profiles and atmospheres in SER and desire format. So you will have a link also to them. So if you are just using Python, just try to follow what I do here, and then you can reproduce it very easily with Python. Okay, so then let's bring the terminal. I will try to put, so let's make this, let me become a bit smaller. So then, and then just put here the terminal. Okay, so then I'm in the correct folder. Yes. So then the first thing we're going to do is to just read the file, data cal and probe. Okay, and then if we do help, wave and SI, so we have that we have read this file called atlas.dat, and then we have wavelength and Stokes height. So as it is an atlas, there's no Q and U and V. So we are, for this example, we are just going to work with intensity, but it's fine for what we're going to do. So then, now that we have these two arrays, so then just let's make a plot, okay? So I will put here stop, and then I just run these, and then we have to the next stop. So we stop in line 28, and we have created a figure that is called Atlas-1 EPS. I will put all the figures in the same folder, and I will put them as a EPS or PDF. So I think PDF is probably easy to just move around. And this is what we have. As I said, we have the two iron line transitions. So this is 6301.5, 6302.5, two lines in the middle that are much narrower. So this is because they come from the Earth atmosphere. And then the intensity goes from 0 to 10,000. So then again, this is a normalization. It could be counts, as if it comes from an instrument. You can have, for example, 40,000 counts, 35,000 counts. And these, we cannot use it for embedding with SR and desire. We have always to normalize it to the local continuum, in the sense that it should move between 0 and 1 or 1.5, okay? So then the first thing is to normalize this atlas to the local continuum. So if this were an observation, my recommendation is to take a patch of maybe 10 by 10 or maybe 100 times 100 pixels, covering a quite sun area. So then you take and you average the intensity profile, well, in this case, the continuum intensity of those values, and you get an average continuum intensity from a quite sun area. In this case, we have the atlas profile that we can assume that is similar to that because there's no special resolution, so probably it was the average of a very large area and hopefully quite sun. So then our profile corresponds to an average profile. So we can assume that continuum values, they correspond to an average continuum from a quite sun region. So then, in that sense, the continuum intensity that we can use for normalizing, it can be, for example, the first point. So if we go to the terminal and we just go ahead, we have that we can use the first point as a normalization value that it says that is 9,832. Or if your profile has noise and maybe it has a lot of fluctuations, maybe it would be better to just take a few pixels in wavelength and take the average over them. So not only 1 point, but maybe a few points. So for example, in this case, we can compute the average of the first 6 wavelength points that are corresponding to the continuum, and then we can print that. And you can see that it's, in this case, it's very similar because as it is an atlas, the noise is really, really small. But in normal observations, you probably will have some variations. So then maybe it's better to just take a few pixels and as a normalization range. Okay, so then with that, we just take our input profile. Imagine that you have a cube of stocks profiles and you divide all of them by this factor. Okay, and I'm going to name it with a different name just to keep things more clear, and also for using it later for comparison. So then this SI norm is the stock size that we have as an input normalized to the continuum intensity. Okay, so then the next step is let's create a profile file with this atlas profile normalized to the local continuum, because this one we can use already with SER and with desire. So if you remember, for that, what we have is we have to create an ASCII file with 6 columns, with the first one, the index. This is the index that we use for defining the line in the atomic file that usually we call lines LT or lines non-LT, and it should correspond to that. So for example, in this case, in this folder, I added this lines LT that we are going to use later. And we have here that we have line 1 and 2, and line 1 is 601.5, and we are going to use them as a blend. So then we just need to create one entrance with the index 1 and add all the stocks profiles. Okay, so then for that, this is the first one. The second one will be the wavelength, and it should be, as I said here, in milliarmstrong, and also referred to the center wavelength in rest of the line related to the index. So let's say another way, you have to renormalize your wavelength vector, put it in milliarmstrong, and respect to this value. So because now it starts on, let's say here, if I set print wave 0, so the starting point is 6301, but we need to have it from like minus 500 milliarmstrong to 1.5 milliamp, 1500 milliamps or something like that. So then we need to subtract this value to the wavelength vector. Okay, and then the third, fourth, and fifth, and sixth values, the columns, are just the stocks profile. So I, Q, U, and V. Okay, so then let's start with the first one, that it will be the index. So for that, what we are going to do is we are going to create an array of 1, because as I said, we are going to refer the inversion to this line. So this line has index 1. And then we are going to create the array should have the same dimension of the number of elements of the wavelength vector. Okay, so we have already loaded the wavelength. So we just compute the number of elements and we just create an array of 1. Okay, and then in the case of the wavelength, that maybe I was already confusing you before, here I hope you will see it much clearer. So we have that the wavelength, the original wavelength vector from the web page, the BAS 2000 web page, we just subtract the center wavelength of the 601 transition and state it here. So this is the one that we need to use, because this is the wavelength the code will use as a reference. And then we multiply this by 1000 to have it in milliamstrong. Okay, and then with that, we can just save the file. And as I said before, I'm always using IDL, but I already create a set of functions that will follow the same method of these files to create desired and set ready profiles, atmospheres, and other input files. And in this case, you can use writeprof, the function writeprof, inside this readwrite.py that is in this link. Okay, so you can just almost follow this script, but just replace the IDL instructions by Python instruction. Okay, so then with this we write a profile. This is the name, and then the index vector, the wavelength in milliarmstrong, and then the stocks profiles. But in this case, as I said, we don't have Q, U, and V, so then the easiest thing is just to put the stocks I but multiply by 0. So then it will be 0. Okay, so if we continue a bit more, then we can have these profiles, and as you can see, it's index, that is going to be always 1. Then the vector, so now it's starting from minus 500 milliarmstrong. Then the stocks I values, and then 0 for stocks Q, U, and V, because we only have the intensity profile. Okay, and this we can already use it for inversion with SER. Okay, so then just let's take a look at it. So we are going to plot in this figure, Atlas-2, we are going to plot the same wavelength vector, and now we are going to plot the intensity normalized to the local continuum. So if we open this figure, we can see that it's essentially the same as before, but now it goes from 0 to 1. Okay, and here it's important to realize that, as I said, this is similar to an average profile, and then it makes sense that the continuum is exactly 1. But the idea is that if you have a map, for example, with granules and intergranules, then you expect that the rest of profiles, for example, from a granule, they have a continuum intensity that is a bit higher. dose from intergranulus, the continuum intensity should be smaller. And if you go to a umbra, for example, then it should be much, much smaller. Okay, so in this case, is 1 is because it's exactly representing the average profile. But then in each individual case, you will have variations of the continuum. Then, as I said, now we are ready for inverting the profile, but I want to add a different step before doing inversion. So in fact, inversions are going to be done in the next tutorial. So what we are going to learn now is, okay, someone has given you the observation. You have, for example, in this case, intensity profile, but they tell you that it was taken at, for example, 0.7 heliocentric angle. So then the idea is that if you normalize only as we did now, it's like normalizing assuming that it's the center, because as you move to the limb, you have the limb Dagnerin effect, where the continuum intensity and also the shape of the line is changing. So the continuum intensity is dropping, and also the shape of the lines, they change. So then if you don't account for this effect, then your temperature and probably also another atmospheric parameters, they will have an offset, simply because you are not including the projection effect of moving to a different heliocentric angles. So we are going to learn how to correct for that. It's going to be very easy. And the idea is that we are going to create after that another profile, and then we will save them, and then in the next class we will invert the normal one and the one that we have account for the heliocentric angle, and you will see how this translate into different inversion results. Okay, so then I added just a link to Wikipedia in case you want to just have a basic grasp of what is the limb Dagnerin and why it appears. And then, as I said, we can correct this in different ways, but I think we have a straightforward option that is relatively simple. And what we have is that Zer and Desire, they normalize the Stokes profiles based on the HSRA atmosphere. So it means that a continuum of 1, a local continuum of 1, it's a intensity profile that has a temperature that is very, very, very close to that of the HSRA atmosphere. And the good thing is that in the HSRA paper, this one here, that in fact I included in the folder, now we are going to look at it, they also have tables, tabulated tables, where they have how the intensity of at a given wavelength changes with heliocentric angle. So then we can use this as a reference for computing how we need to rescale our continuum intensity, that now we are assuming that is this center, how we need to rescale it to a different heliocentric angle. Okay, so then this paper, that is a very, very interesting one that I fully recommend you to check it. It has a lot of tables, but we need to go to the table 6. Okay, in this one I will make it a bit bigger so you can see it. So in this case we have a lot of things, but the important thing is in the top part is the wavelength in Armstrong. So then in this case we need to move to 6,000, that is close to 6,300, that is what we have now. And then we have 2 columns. Okay, so in the description it says that the first column is the specific intensity, and here we have the units. And then in the second column it says that is the intensity ratio with respect to the descender. So what we have is that here is how the intensity changes, and then here is the ratio of how it changes. So for example, in this case, this value should be equal to the ratio between these two. So in fact, I did it here. So I took the value of this column. So this 8.9776 is this one. And then I also print close to it this ratio. So the ratio between this value and this value on top. Okay. So if we do this, just let me type, and then here you can see that the value that it's in the second column is equal to the ratio of the first and second column. Okay, sorry, and the first and the second row of the first column. Okay, so then it says, it means, okay, nice. We just want to have which is a fraction of darkening that we have from one heliocentric angle with respect to mu equal 1 to the center. So in this case, we have mu 1, mu 0.8, 0.6, 0.5, 0.4. And with just this column, we can have this, how we need to rescale the intensity profile. But the problem is that we don't have very continuous grid, so it's every 0.2. Here the step is a bit smaller, but in the top is every 0.2. So I think it's probably better to do an interpolation and then have the option, for example, for 0.7, 0.95, and then it will be much more accurate. So then my impression for that is that it's better to use the first column, because in the first column you have intensity values from mu equal 1 to mu equal 0.1, while in the case of the ratios, the first value is a different element because you cannot compare it from itself. So I recommend you to just use the values of the first column and then compute the ratio with interpolated profile. Okay, so then let's do it. I know I'm talking too much, so maybe I'm a bit misleading you. So just let's minimize this. And what I did is the following. So I took the intensity values of the first column. So this is for mu 0.1, and then this goes to mu equal 1. Okay? And then I saved the associated mu values. So 0.1, 0.15 until 1. Okay? And then I said, I want to have more precision and I want to have a step of 0.01. So if someone says my heliocentric angle is 0.76, then you will have the option to reach that precision. You can even go further, but I don't know if we have so much precision in general with defining the heliocentric angle of the observation. Okay, so then here we have that if I print this mu nu 0, it's 0.1, okay? Then the last value, the index 90, it's 1. And then if you subtract the difference between one index and the previous one, you will have that is 0.01, okay? So then we have a new vector, a mu vector, that covers the range of values provided in the table on the HSRA atmosphere, but with a much finer step. Okay, so then we can interpolate the original intensity values with the original heliocentric angles, and including the new heliocentric angles, and then using a spline interpolation. Okay, so if we go to this figure, that is HSRA certain to limb continuum. Let's open the PDF. What we have is that our new vector is the squares, and the original one are the red crosses. So we have that. You can see that it seems that the interpolation is relatively good in terms of smoothness, but as you can see now we have much more points. So then you can have the option of selecting different heliocentric angles. Okay, so just make it a bit smaller, and again we started just with the reds, and now we have all the squares. So then if someone says, okay, this observation was taken at mu 0.71, so then we have already normalized to the local continuum using, imagine, the average intensity profile or average continuum from a Poisson area. But now we need to project this to a different heliocentric angle, in particular 0.71. So then it's relatively simple. We print or we look for the index in our new mu vector that corresponds to this heliocentric angle, that in this case I already looked for it, and is index 61. So at index 61 our mu value is 0.71. So then the factor that we need to use for normalizing, rescaling our profiles is the intensity at mu equals 71 by the intensity at mu equal 1. That is what we are assuming now. So then with this value, we can just print it. You will see that it's smaller than 1. So this value that is 0.84 or 85, we need to multiply our entire stocks profiles, I, Q, U, and V, for this value. So then we can include the effect of the limb Dagnerin. Okay? So then in this case, I'm going to call it now SI normalize 0.71. That is the one that was normalized to the continuum, to local continuum, and also multiply by the ratio. Okay? So then in this figure, Atlas -3, we can open it and we can see that the original one is the black. So this is assuming this center. But now if we include the effect of the heliocentric angle, now you can see that the continuum has dropped, and also the intensity of the lines is also affected. Okay? So then the idea is that later on we will check what happens when we invert the black line and the blue line, because SER and desire, they always assume line of sight. So if you don't tell the code otherwise, it will assume that you are looking at this center. So if you are at a different heliocentric angle, you need to project and take into account the effect of the heliocentric angle to just tell the code that your line of sight is not exactly mu equal 1, and is mu equal 71. So in principle, what we are doing now is just rescaling the profiles, including this effect. Okay, but as I said, it's very important. Just see how changing to 0.71, that is not so bad. It's not the center, but it's not so bad. But you can see how it changed a lot, and this it will have a big impact in temperature and velocity. So then now let's save the profile again. So it's the same method. So we will use the same index, the same wavelength that again is in milliarmstrong, and also respect to the line center of the line of interest, in this case 601.5. Then we have the stocks I, and then the other profiles are 0 because we are just observing the atlas, okay? Or we are going to fit the atlas. And then before having everything ready for the inversion, we also need to create the grid file. And I think now is the best moment because we have the ingredients already. So then if you remember, the grid file was a file that looked like this. So you had to provide the index, you had to provide the starting wavelength, the step, and also the final wavelength. And this is something that we have already because we are using it for creating the profile file. Okay, so then we're going to print the initial step, that is the difference between the first and the 0 point, and then the final step, that is the difference between the last 2 points. So just let's move ahead 1 second. And then we have that in the leftmost side of the wavelength vector, the difference is 2 milliarmstrong. And in the final side, the difference is also 2 milliarmstrong. And I'm doing this because it's not always clear that the wavelength vector is uniformly sampled. And if this is not the case, then we need to interpolate to a uniform wavelength grid for SER and desire. Okay? So then again, your wavelength vector should has a step difference, a sampling that is uniform. The value is not so important, but it has to be the same from the beginning to the end. No, sorry. And then the idea is now we can also print the starting point of the wavelength, that in this case is the same that we are using for creating the profile file, that is minus 501, and then the final wavelength, that is this one, that is almost 1500. Okay, so then with that we can create our grid file that will have this initial wavelength, this step that is 2, and then the final point that is 1500. And then, as I said, we want to treat the full spectral window that we selected as an entire spectral region. So we are going to consider that the lines are blended. That is how we define it. And for that, what you have to do is to include all the lines, all the index of the different lines included in this spectral window. In this case, it's only 1 and 2, separated by comma. Okay? And then the important thing is that the wavelength values that you provide here are always respect to the first index. Okay, so then it's going to be very different to put here 2,1 or to put 1,2. So then just be sure that your wavelength vector is referred to the index that you put first on the wavegrid file. Okay, in this case we're using 1 as a reference, so then 1 should be the first one. Okay, I think that's all for today. I don't know if I went too fast, but I think I wanted to go relatively smooth, but just focusing on a few things. And those things are, when you get an observation from any telescope, usually this is in counts, usually related to the sensor counts. So then you need to normalize this to the local continuum. And for that, my recommendation is to take a few pixels that correspond to a quiet area, as quiet as possible, and then average the continuum values over this region. And then with this average continuum value, you divide all your profiles or your wavelength points by this value. So this is the first normalization that we did. And then the second step is that is fine, but only if you are very close to this center. If you are far from this center, you have a different heliocentric angle, then you need to rescale this, because otherwise your line of sight is not the one the code is considered as line of sight. So then the easiest way is, as we did, go to the HSRA paper, to table 6, look for the wavelength that is close to your spectral window of interest, then also look for the intensity values that are close to the heliocentric angle that you have. If they are not available, just do an interpolation as I did. Then you need to compute the ratio between the intensity at your heliocentric angle respect to the intensity at heliocentric angle mu equal 1. And from that you will get another scaling factor that you use for multiplying your full profile, so your full Stokes vector, your full array. So then you are including the effect, the Lim-Dagnerin effect, due to the heliocentric angle. And then with that, you will avoid having offsets in temperature or maybe even velocity due simply to the different line of sight that you are using because of the heliocentric angle. So then, in the next tutorial, that hopefully it will come soon, what we're going to do is first, we're going to invert the intensity profile without this normalization, then the profile with the normalization at, assuming, for example, 0.71, and you can see the differences in temperature and velocity. And then we are going to remove the telluric lines and to check how this affects the accuracy of the inversion, and also learn how to do it. Okay, so I think that's all. I hope you like this type of tutorials. I hope also the video quality and the sound is good, and I hope you find them helpful and you would like to continue listening and seeing me through the screen. Okay, thanks a lot and see you soon. Bye.